So welcome. So we're going to talk about image formation today. And basically this consists of a few skills and then different applications of those skills. So we're going to learn how to do ray diagrams. And there's basically, there's 3 drawings for the concave mirror. There's 2 or 3 drawings for the convex, depending on how you count. And then there's a couple of drawings for the converging lens and a couple of drawings for the diverging lens. So there's maybe 10 drawings altogether. But there's only a few rules. So if you learn how to do the rules, you don't have to learn the drawings, you just have to learn the rules. And then they go very straightforwardly. And typically on a test, I will ask you for one of those drawings. I'll give you the beginning of it and I'll say, finish this drawing. And then the other thing you can do is do that mathematically. And so there's that many different calculations, but they're all using the same 2 equations. And again, there's all these rules for the signs. It's not the equation that people make a mistake on. It's the signs. And it's like a lot of things that are just a bit arbitrary. You can't intuit things from first principles with the signs. You could, but it'd be very hard. Sign convention is there just to distinguish between a concave and a convex mirror, to distinguish between whether your object is in front of the lens or behind the lens, and so on. So it's going to seem like a whole bunch of stuff, but when it comes down to it, there's basically I'd say about 6, maybe 8 rules you have to remember in various forms. Some of them are obvious and some of them are not. So it's just spending enough time on it, enough practice on it that it's easy points. It's just getting to the stage where it becomes easy points because you're familiar with it. So here's good old Newton's diagram. I mean, I drew this, but Newton drew it before me. It's this traditional diagram. We have, an object that's above my head, and I'm looking into the mirror at it, and the rays of light come from the object to the mirror and then into my eye. It's amazing how when we're all not thinking about it, we tend to draw the rays the other way, like we look, whereas we receive light. It's kind of interesting, really. It's just psychologically. Vision is a receiving science. It's not a perceiving science. You might choose to receive from one direction or another, but X-ray eyes, clearly don't exist. But the way we show X-ray eyes is this beam penetrating from the eye. It doesn't work like that. So this is a nice figurative diagram. It kind of shows that because the light bounces off the mirror, it actually appears as if it's appearing back here. But there's a wall behind there. It's a mirror. There's like something behind it. So it's like, obviously the object is not there. So our image is not the object. It's a perception of the object. Okay. But that's a lousy way of doing these diagrams. There's so many problems with this. It's very hard to draw that diagram, and it's not that informative. This is a much better way of drawing the same diagram. It looks much more abstracted, but it is much better. And what we do, first of all, is we establish an optical axis, sometimes called a principal axis. And we stand on the principal axis an object. We typically will put the object at the left of our element. Our element in this case is the mirror. And we let the light, there's light going from the object in all directions, and we only pick a few rays. One ray goes from the bottom of the object and hits the mirror at 90 degrees and bounces back. So I could draw that in. I didn't draw it in on the original, shame on me, but I could draw that in like that. There's a million other rays I could draw, but that's an important ray because it tells me where the bottom of the image will be. And then we take 2 more rays. One from the bottom tells me where the bottom is, but it doesn't tell me where along on that line that the bottom of my image is. I need 2 rays from the top to cross over and tell me where the top of my image is. One of the rays, well, let's do the same thing. Let's go 90 degrees to the mirror, and then we're going to go back again. So, and then a third ray, I'm going to say, well, if I go from the top of my object to the principal axis, I'll bounce off at the same angle because of the what we learned in the last class, which is angle of incidence equals angle of reflection. And these three rays never cross. The two red ones and the green one never cross. But that's not the end of the world. We just back project. So I back project my red one at the top. I back project my green one. And they appear to cross here at this point here. And so that's where my image is. It's behind the mirror. And that's when you look in a mirror, the person seems to be behind the mirror. You know, it's like, okay. So it's termed virtual. Not meaning it's good, not virtuous. It's like, you know, hey, it's kind of there. So we have two types of image. We have the real image and the virtual image. And one's not better than the other. The difference is that in a real image, the light rays truly cross. And in a virtual image, the light rays do not truly cross. We can see both of them. We can't tell by just looking, is it real or is it virtual? I don't believe. We can tell if we put a piece of paper where we think the object, the image is. Because clearly, if I put a piece of paper behind the mirror, it's not going to show the image. So you cannot form an image on a virtual image. A virtual image can't be projected to a screen. You can't put a piece of paper there and see it. But you can put a piece of paper where there's a real image and see it. So how can I see a virtual image? Well, I can see a virtual image because I'm not a piece of paper. I got an eye, and the eye has a piece of paper like my retina, but a lens in front. And so that lens enables you to form a more complex viewing system. So it's important to know if it's a virtual or real image. But for many practical purposes, the distinction is not so important. If you want to form it on a screen, then you've got to know, and it is important. But if you want to look at it, you can look at both of them. The important thing to recognize is the fact that, you know, technology is way beyond the single lens or the single mirror or whatever. We're dealing with, I mean, just in my lifetime, a camera like the camera I have on my iPhone, which is as small as that, is just unthinkable. I mean, this is amazing technology. And most times you're dealing with many elements in a lens system. And so what is the image for the first element is the object for the second, and what is the image for the second element is the object for the third, and so on. You just work your way along. It's relatively simple. It's just step after step after step. And so if it's a virtual image, it becomes a virtual object for the next element. And you got to kind of know it's a virtual object, not a real object, because the math changes. This is quite practical. One of the problems they have, from what I gather, in jet aeroplanes, fighter aeroplanes, is that the people have to look at their controls, or they have to look at their canopy or whatever, and under certain light conditions, if they're not careful, you see your own reflection. That's the last thing you want when you're trying to maneuver and all that kind of stuff. So, for instance, they can solve that by making the front of some of the controls a certain shape, so it does not form an image that you can see. There's reflection. There's going to be an image, but so optics are kind of used all over the place. Sometimes you recognize, oh, that's an optical element, and sometimes it's designed cleverly so you don't even notice it, but it's based on optics. And then we get other disasters, like there's a building in Los Angeles and a similar building in London, and they decided to make the south-facing wall glass and concave. They call it the cell phone building in London. Well, south-facing glass faces tend to reflect a lot of sunlight, and when you make it concave, you concentrate the sunlight, and so they've been melting cars in London. In London, imagine it. I mean, you know. And the worst was a similar type of building was constructed in Los Angeles earlier and had burned people in the swimming pool of the next hotel over. And it's like, what's going on here? I mean, this is like 2000 and whatever it is. And we aren't even thinking about this as architects. I mean, this is like the last thing you want to do. So optics are kind of like in many places. Sometimes you notice them, sometimes you don't. We take so much of this from Newton. And I think Newton actually developed the terminology of using P and Q. So P is the object distance and Q is the image distance. Do you know that old saying, you got to watch out for your P's and Q's? Have you heard that? It means pay attention. Don't get things confused. And the reason it comes from printmakers, newspaper typesetters. When you're setting a newspaper, you have to pick the letters out, and the letters are all backwards because you want to print it the right way around on the page. And so rather than having A, you have A. And rather than having G, you have G. And you get pretty good at it. But the problem comes with P and Q, because they're kind of like, a newspaper doesn't have the little edge on, the little tail on. The little tail is there for a reason, for people like me, who get these things backwards. I've always been a little bit dyslexic like this. I'm not dyslexic. It's like it's people suffer far worse than I do. But for me, it comes in. And I have trouble with B and D, which is why on a multiple choice test, I always use capital A, capital B, capital C, capital D, because it's obviously the way to avoid it. And Newton should have done the same thing. And you think somewhere in the last 350 years, somebody would have had the common sense to write a textbook that didn't have little p and little q in it, but they never have. So I will tend to write things down as big P and big Q, certainly when I'm doing the problem. And if you feel like you want to do the same thing, I understand entirely. Okay.
What are the green lines on the bottom represent?
The green lines on the bottom. This guy?
Yeah.
That's the ray coming from the top. Okay. It bounces off and comes down the bottom. Yep. And remember, we only picked 3 rays out of all those rays that were possible. The other thing we have is H is usually the object height and H dash is usually the image height. And what we want to talk about is the image virtual or is it real? We talked about that. Is it upright or is it inverted? And is it magnified or demagnified? Magnified being bigger than 1, demagnified being less than 1. Okay. So now we look at some curved mirrors. The best mirrors for what we want to do are probably parabolic mirrors, but they tend to be expensive. And if you're going to just use the middle bit of the mirror, if you're not going to use a particularly big mirror, just a little bit of the mirror, and it's not too curvy, you can get away with a spherical mirror. It makes the optics a bit cheaper. So we draw it like this, although we will not do our ray diagrams like this. This is an illustrative drawing. So we're imagining a spherical mirror. It's got a certain radius. What we find is if we send a whole bunch of rays parallel to the principal axis, for small segments, not if we do a very curvy mirror, but for small segments, they will all be reflected through a point of interest. And that point of interest is halfway between the center of curvature and what's called the what's called the, I can't remember the name of it now, it is called the, yes, yes, I think so. It's on here somewhere anyway. Anyway, where the principal axis hits the mirror. Center of the spherical segment. Okay. And we named that the focal point. So, okay. That's a useful kind of point of reference. It's halfway between the center of curvature and the mirror, basically, along the principal axis. We say C is the center of curvature, V is the center of the spherical segment, F is the focal point. I will talk about F as the focal point and F as the focal length. It's just contextual. You just got to figure out which one we're talking about. Focal length being that distance. Maybe that's why he uses little f, I don't know. And the CV line is the principal axis. It goes on forever, basically. Rays travel parallel to the principal axis are reflected through the focal point. Okay. Now, when we come to draw these diagrams, and I apologize, I used to have these all on a separate page, and I went through this phase of trying to get my notes more condensed, and so I put all these on one page, and I think it's just a little bit small now. But you see the overarching principle, anyway. We don't draw the curvy mirrors, because the curvy mirrors, when we actually try and draw the ray diagram, don't work. We imagine the little bit of the mirror is the bit we're actually using optically, so we actually draw it as a straight line. And if it's concave, we draw it like that. And if it's convex, we draw it like that. And we imagine the paint on that side. When I was a kid, when I was learning this, I was told to put the paint on the back side of it, you know. Okay. I don't anymore. I just draw it because I know which one it is. We tend to go from left to right in pretty well all cases. If you think about it, so this curvy mirror has a focal point and it has a center of curvature, and they're like rulers on this, measuring distances on this outside. So I've got three choices. I could put my object there, I could put my object there, I could put my object there. Why don't I put it actually on the focal point? Because I will get no focus with that. Why don't I put it on the center of curvature? Because I'll get no focus with that. And I did it for the other class. I'll nip out, during our break, I'll nip out and get the big mirrors. And you can walk backwards and forwards to a concave mirror. And you'll see you're in focus, and then you go out of focus, then you go in focus, out of focus, in focus. So you'll see that. Okay. Okay, so how do we draw our ray diagram? We take a ray and it goes along the bottom, hits the mirror and bounces back. We take a ray which goes parallel to the optical axis and goes back through the focal length, through the focal point. And then our third ray is the harder one to draw. It's supposed to go from the top of the object and hit the mirror at 90 degrees and bounce back, because it's a curvy mirror. But it don't look like 90 degrees to me. And so you just draw it. Goes through the center of curvature, through the top of your object, draw your line. So don't worry about how it hits the mirror, just draw it. Those three lines will never cross. Well, those two lines will never cross, so we back project, and there's our image. And so it's virtual, it's upright, and it's magnified. Yep. I back projected that as well. Where the two upper ones cross is where my object is. It's virtual because the light doesn't actually get behind the mirror. It's upright because the head of the arrow is pointing upwards, and it's magnified because it's bigger than that blue one there. And you move it out. And you do the same three rays. That one goes all the way like that, and then this one goes along here and comes down through there. And this one goes through the center of curvature and the top of my object. And these guys do cross. So I've gone from being nearer than the focal length to being farther than the focal length. And things have changed a lot. This image is real. I could put a piece of paper there. And if it was if it was a bright object, I would see the light. If it was just a wooden arrow, I wouldn't see it on a piece of paper. But if it was a torch light on a piece of arrow, if if it was illuminated, I could form an image of it.
So do the images only form when two rays cross?
They're formed at that point, yes. Because you know, if the mirror's doing its job, it takes rays from the top of the object and takes them to the top of the image. So if I take two different rays, where they cross, that must be where my image is, because they're never going to coincide again. Yeah. So this is real. It is inverted. It's upside down, and it's also still magnified. Okay. And then I put it even further out, and I get my mirror. I get my bottom ray goes backwards and forwards, and my top row goes parallel to the optical axis and then goes down there through the focal point. And then this other ray again goes from the top of my object to the center of curvature and goes down. And they do cross again. And we can see now that my image is real, it's inverted, and it's demagnified. Complicated diagrams, and you might well want to practice them, but the rules are pretty straightforward. Yeah, the rules are pretty straightforward. Notice how the image bounces around. It's virtual, it's massive, and then it's inverted and it's real, but it's a long way away. And then when you move even further away, it's inverted and it's real, but it's closer by. So there's some complicated behavior goes on with mirrors and lenses. We tend to oversimplify them in our day-to-day lives. I get readers and it says 3.25 on these readers. Well, that's correct for when I put them on the end of my nose. But if I set that same lens and put it further from my eye, it's giving me a different magnification. Maybe it's working, maybe it's not working. Maybe it's inverted, maybe it's right side up. So there's not a simple pattern, as far as I can see, to figure out what the image will do. So I tend to I sketch ray diagrams quite often when I'm dealing with optics. Once you've got the hang of it, they're straightforward. If I do a convex mirror, then the center of curvature is behind, and so my focal length can be behind. And now what's happening is that the ray, again, on the bottom goes to the mirror and goes back again. The ray from the top, the first ray which goes through the focal, goes parallel to the optical axis, and then was bounced back through the focal length, is now parallel to the axis and goes through the mirror. Well, it bounces off in that direction, I'm sorry. So that goes like that, and then it goes up like that. And then the other one, which goes from the top of the axis and goes through the center of curvature, again, hits the mirror and bounces back again. And these guys never match up, so we back project them, and there's our image. So, because the focal length and the center of curvature are behind the mirror, we deal the rules just the same. We just recognize that the focal length and the center of curvature are behind the mirror. And it turns out if I go, that was when we were inside the distance of the focal length. Now if we go to the next one where we're inside the center of curvature, which is this guy, the same thing happens. It's slightly different in size, a bit smaller in fact. And if I go a long, long way away, it'll be even smaller, but it will always be virtual, upright, and demagnified. That's just the way it is for convex mirrors. Convex mirrors tend to be used in, where have you seen convex mirrors used? There's two places in your life when you've probably seen them a lot.
Truck mirrors or tow mirrors?
Truck mirrors or car mirrors, yeah. They're both the one inside the cab and the one on the outside the cab are convex. It says on them, you know, objects in your mirror may be closer than they appear because you're getting it demagnified. So you glance and it looks, oh, that's 20 yards away. No, it's like, 5 yards away. And anywhere else you've seen convex mirrors?
Parking garages or around corners?
So you get them sometimes on people's driveways if they want to kind of look and they've got a blind driveway. They'll sometimes look in a mirror. They'll put one up in their garden, or you may see them garages.
Yeah, so you can like see around the blind corner.
Yeah, and also stores. You see them in stores and Publix. If you look up, they have them. They sometimes have even cameras behind them because they're not a completely silvered mirror. We say silvered; it's aluminized, but it's not completely silvered. There's light does get through, and they have a little camera there that will look around. But it's also so people can glance up and see somebody in the next aisle. Sorry? So in the gym, so I don't know about the gym, but I once bought a bedroom full-length mirror, and it was only that wide and that high, and I looked great in it. I looked like I'd lost about 10 pounds and really tall. And then I got hold of it and flexed it. And I don't know if that was just the way mine was, or whether it was some really clever advertising person was, oh, he'll like this, you know. But it cheered me up every morning. So yeah, sometimes, yeah. So know these. Oh, and then concave mirrors. Where have you seen concave mirrors? We've often got them around the house. Maybe not at your age, but certainly at my age you do.
Like a hand mirror.
You don't have one. You don't have a concave mirror. Or you might, but you don't use it.
Like a shaving?
It's a shaving mirror, yeah, a shaving mirror. I don't know, how many people here use a shaving mirror? I must admit, I cut and feel. And I kind of like feel for the stubble and then go for it. But that's partly because of the when I was I keep telling you about when I was a kid. When I was a kid back in the 60s, when I started shaving in 68, it was a single blade. You'd simply buy a blade and you'd take it out and you'd shove the thing into your thing and and that thing would cut you to pieces. It was, especially for an adolescent where your skin's like blotchy and like, it was a disaster. And it was only passed by my granddad. My granddad would take his, they call it a safety razor because the alternative was was like a straight edge razor, which was, I mean, you'd get fights in the street, people would kill each other with those things. Like when you go to the barbers. And so my granddad would take the blade out of the safety razor, and he would put it, to keep it clean somehow, he'd put it in the soap dish.
I've seen people, yeah, it's called like straight edge.
Pardon?
They call it like straight edge, or like edge shaving, where you just like put it in the soap dish and you just
Oh, I see. So my grandmother put the soap on it, and then my dad came in as a little boy, covered in dirt. My grandmother kind of like had hold of him, and he was wriggling, and she got hold of the soap, and she went down the back of his legs, and she took a layer of skin off his head. So, watch out for that. And also, how many people, makeup mirrors, same kind of thing. It's, so next, let's do it mathematically. So we have really just two equations. 1 over P plus 1 over Q equals 1 over F. And that, 1 over F equals, well, 2 over R, because the focal length, the distance from the center to the focal length is half the distance, which is the radius. So, that's where that comes from. And then we'll talk about magnification in a minute. Well, we'll talk about it now. So the magnification, which is the image height over the object height, is equal to minus the Q, minus the image distance over the object distance. We've got to be careful about sign conventions. So P, the object distance, is positive if the object is in front of the mirror. Well, that's where I expect the object to be. If it's behind the mirror, it's not very much use, but, well, unless it's a virtual object. I can project a virtual object behind a mirror. The light's still coming from the front of the mirror, so it works. So I can have an object behind the mirror. But most of the time it's in front. So, well, that's positive. And P is negative if it's the other way around. I would not learn both of these. I would say if it's the opposite, it's going to be the opposite sign, you know. So there's three things to remember, you know. Q is positive if the image is in front of the mirror. That's kind of where I expect the image to be, although sometimes it's not. So that's positive. And then the focal length and the center, the radius of the mirror is positive if it's concave. That's completely arbitrary, but it goes with these other two, so you've got to keep the three together. And again, if it's negative, if it's not. So learn it's concave, it's positive. That was the first thing we dealt with, concave before convex. And if the object is in front, if the image is in front, positive, positive. If it's concave, positive. If M is positive, the image is upright, and if M is negative, the image is inverted. And I'm going to put a page in here, and we're going to play with this. Okay? No, I don't want to. No. Let's put a page in here. Okay. An auto file save exists. Cancel. Okay. Okay. So let's have a look. I'm going to have a 6 centimeter tall object is placed 8 centimeters in front of a convex mirror that has a focal length of 6 centimeters. Where is the image? And I cheat by the first thing I'm going to do is draw my ray diagram. So let's have a look. Focal length, 6 centimeters. So there's my F. And so that means there's my C. And then this is like there. Yeah? Everybody okay with that diagram so far? It says a 6 centimeter tall, don't worry about that. It's just saying it's a certain height. 6 centimeter tall object is placed 8 centimeters in front of a convex lens. There's my convex lens. Convex mirror, sorry. That has a focal length of 6 centimeters. So there's my 6 centimeters. So this is 8, so it's a little bit beyond. And my focal length is behind and my center of curvature is behind because it's convex. Yeah? And then I draw my first ray, and my first ray goes to the mirror and comes back again. And then I draw my second ray, and my second ray goes parallel to the top. And what does it do? Oh, it's supposed to go through the focal length. Well, but it bounces away from the mirror, but it's projected from the focal length, like that. Yeah. And my third one, I've got to do it in black, I'm afraid. My third one goes through the center of curvature, so it kind of goes like that and gets reflected back on itself, because that's what those guys do. But it's projected through there. And where those guys cross, there's my image. Make sense? 90-degree reflections. Remember that we're doing a ray diagram, so we've got to allow ourselves to cheat a little bit. It's not going to look right. Yeah. But it is angle of incidence equals angle of reflection, and this guy here is like 90 degrees reflecting on itself. Yeah. The black one is exactly right. It hits and bounces back at 90 degrees, but it won't look like that on the ray diagram. And the reason is, to make it look right, we have to draw it to scale, and it's going to be impossible to draw. So we're doing an abstraction, basically. So that's told me that my image is upright, demagnified, and virtual. Let's see if that's true mathematically. So let's come along here. Leave it in red. So I'm going to say 1 over P plus 1 over Q equals 1 over F. Now my P, that is 8 centimetres. I'm going to leave it in centimetres. This is one of those cases where I can cheat because it's all in centimetres. I can leave it in centimetres. I know I drum into you. You've got to always go to SI units, and but it's just easier if you leave it in centimetres. I try to remember to leave them in metres, but I tend to think of them in terms of centimetres because that's the scale you tend to work on when you're in the lab, really, to tell you the truth. And then 1 over Q, that's what I want to find out. I want to find out what my image distance is. You know, where is the image? That's what I'm trying to find. And that equals 1 over F. Oh, okay. So I'm going to have to go back for a minute because I've got to check on something. And my focal length is 6 centimetres. So 6. Unfortunately, I've blown over something which is really important. So I've got to stop. I've got to go back. Because this is all about signs. So here is my object. It is 6 centimetres in front of my lens, of my mirror. So is that a positive 8 or is this a negative 8? Look at your sign convention and see what you think. It says, yeah, if the object is in front, it's going to be positive. So that's a positive 8. So my advice is you put down the positive, whether you don't defer to positive if there's no sign there. Be mindful of the signs in this. It's the thing that's going to trip you up if anything trips you up. And then, now, this is a convex lens. So does the nomenclature say that, does the sign convention say it's a positive 6 or a negative 6? It's a negative 6 because it's a convex lens. And you never figure that out from first principles in a test. Actually, you just got to walk into the test knowing that. So 1 over Q is equal to 1 over 6, let's call that minus 1 over 8, which equals, let's use common denominator, so 48, so that's going to be minus 8 minus 6 over 48, which equals minus 8 and minus 6 is minus 14 over 48. But remember, I want Q. So Q is going to equal minus 48 over 14, which equals minus, let's divide by 2. That's going to be 24 over 7, which equals minus 3 and 4 sevenths. Well, no, 3 and 3 sevenths, about 3.4 centimeters. And what's the sign convention for your image distance? If it's positive, it's in front. If it's negative, it's behind. Or we could also say virtual, yeah? So virtual or behind the mirror, and basically a relatively short distance. If that was 6, that's 3.4. So it makes sense, yeah? Let me add a little rider on this. How tall is the image? So I'm going to say M, which equals the image height over the object height, which equals minus Q over P, which equals minus Q is minus 3.4 over P, which was plus 8, which is plus 3 8s are 24, 4 8s are 32, carry 2, 2, 5. Now, How do you know if it's magnified versus demagnified? More than one or less than one?
Maybe less than 1 if it's demagnified.
Demagnified. And how do you know if it's upright or if it's inverted?
If it's positive, it's upright.
Positive is upright, negative is inverted.
Just like on a graph, right?
So, yeah. So, I don't know about you, but I don't feel, I've been doing this a long time, but I still don't feel comfortable just doing the mathematics. I find the diagram relatively straightforward, so I'm always going to do a diagram in the corner of the page. It will get me no points. Okay? Your question or comment?
We just solved for magnification, right? Not how tall the actual.
Oh, I'm sorry. So I'm just, because that's what I'm going to want on a test. So then you turn around and say, oh, in that case then H dash is equal to H times M, which equals, how tall was it? 6 centimeters. 6 times 0.425, which equals about 3 centimeters. Yeah. So in truth, more times than not, I'll ask you for the magnification or whatever.
3.4 centimeters.
I'm sorry?
Wouldn't it be 3.4 centimeters?
I don't care. Yeah, it's approximately. Yeah, cool.
No, I'm saying when it be the answer for. Oh no, never mind.
Yeah. Okay. So, I don't know about you, but I'm probably going to do a little diagram at the side of my page, and it's fine. I don't mind you doing that. It's just it won't get you any points. Because in a test, I'm going to say, using a ray diagram, figure this out. And I'm going to say, using the lens equations, figure out. And you can't swap them. So, and there'll be one of each. It's kind of like, they're both two important skills. So, okay on that? It's easy points. I think it's easy points. It's just spending a bit of time with it. It's not conceptually very hard. Okay, so let's go back here. So then, let's do the same thing for the lenses now. Two types of lenses. The converging lens is shaped like that, and the diverging lens is shaped like that. If somebody's wearing glasses, like I wore glasses all my life until I was about 22, actually. I had big, thick, my eyesight's really bad, and I had big, thick, converging lenses. And so my eyes looked like they were massive. If you see somebody and their eyes look like they're massive, they've got converging lenses. They're far-sighted.
Oops, sorry.
Yeah.
Just listening for the noise.
Okay. There's the projector, but not the fans. No.
Sorry.
Thanks. No, it's okay. The other one is the diverging lenses, and the diverging lenses make you look, you've got like little small eyes, and you can see the people's face. You know, you can see like the face seems to come in where the lenses are. They've got nearsightedness. You get more far-sighted as you get older. So people with near sight tend to improve a bit as they get older, whereas people with far sight tend to get worse. That's not to do with your reading. Reading is all about how adapt your lenses at changing the focal, and that tends to go when you're about 45, within about a week. It's like you can read, and then a week later you can't read. And you go, man, you know, this photocopier needs fixing. I remember telling somebody that. And they said, no, it doesn't. Go and see your eye doctor. And I went, and I said, I can't read anymore. And they said, oh, yeah. But this improves it. Oh, yeah. It was amazing. It was like, I can read again. So very quickly it goes. It's just the muscles in your eye won't contract. Okay. So we don't draw the whole lens. We draw a line for the lens, but we kind of hint. So there's a little triangle at top, which is that little triangle. And there's a little triangle at the bottom for that. And then there's this little, you know, you can see where it comes from, you know, the thing. We have a focal length in front and a focal length behind because light goes both ways through these things. But again, we work from left to right. And we can either be inside our focal length or outside our focal length. We don't have beyond the centre of curvature because it doesn't really apply anymore. And we do the same thing. We draw a ray along the bottom, and it goes all the way through this time. And then we go over a ray, and the ray goes parallel to the principal axis, and it goes through the far focal length, doesn't get bounced back. And then the next one does not go through the centre of curvature, because there is no centre of curvature, but it does go through the centre of the lens. And these guys never join up, so we back project, and here we have a upright, virtual, magnified image. And that's what you get with the magnifying glass. Magnifying glass, the object has to be closer to you than the focal length of the magnifying glass. So you tend to hold things close and you use a magnifier to look at it. If I go beyond that, then everything flips and I get a inverted, magnified, real. This is a real image. This is why we don't tend to hold lenses up when we want to look at the distance. It's actually, you don't always, it depends on the actual position whether you get it magnified or not magnified. But it's going to be upside down, it's not going to be very good. We don't take a magnifying glass and look at a car in the distance and read the number plate. It's harder than that. If we have a diverging lens, then the focal point of interest is the one that's in front, because we diverge from it. We converge on this focal point, and we diverge from this focal point, but otherwise the rules are the same. Do you have a comment or a question?
Yes. Why is it real and why is it virtual in that case? Because in the other ones it was virtual when it was on the other side of the...
Or because the rays do actually go through this point. A mirror, in a mirror, the rays are bounced back, but in the lens, the rays do get transmitted through. So yeah, so it's logical from the diagram, but it's like, you know. So I find lenses, I can't just, if you told me, if you stopped me in the hallway and you said, will the image be real or virtual? I have no idea. I couldn't tell you, but I can draw the diagram for it. So I tend to get my stuff from the diagram. I think I know one person who can do that. Yeah.
Now, like, for the, let's say like real application, like
Yeah.
would a virtual image, like looking at lens, would it be something that's on like you seeing from like this, like from like being reflected, or?
So, I could take this virtual image and I could use it as an object for another lens element. I could, for example, put a lens here and raise, I'm digging a hole for myself. I could put a lens here, and I would, for this lens here, I would use that as my object. I'd have to define it as a virtual object in my math, but I can certainly play with it. Yeah. And that's done a lot with like zoom lenses. That first element forms an image that's way beyond like 3 other lenses. And so it's like, oh, okay, you're messing with it. So it works. It's a little bit hard. I think unless you do this for a living, it's a little bit hard to do the more complex systems in the least bit quickly. I think you can apply this thing. If you get a big enough piece of paper and you go step by step, you can actually find the final output for a complicated system. But you'd need to go step by step and big piece of paper. But the rules don't change. They're just added on top of one another. And then don't worry about this thing in the middle. This is our old friend. It's the same equations again. And we just say, well, now we've got to be careful. P is positive if the object is in front of the lens, and it's not otherwise. This is the switcheroo on you. Q is positive if the image is the back of the lens, because it's where you expect the image to be. So that's new. That one's a switch from the mirrors. Yep. And then R1, oh, don't worry about that. We'll get back to that. And then F is positive for a converging lens. Again, we did the converging before we did the diverging. So remember the order we did it in, or learn it one way. So it's basically the same, apart from the fact that the image is, the signs have switched for the image. Okay? I've just got to check on this. Okay, I got time. Yes.
For setting Q is negative if the image is, is positive if the image is in the back.
Yeah.
Okay, maybe I was reading it wrong first. Okay, no, that makes sense.
Yeah.
Okay.
It's where you kind of expect the thing to be. And if I do, well, let's talk, I've run out of time, so let's talk about this next bit and then we'll do an example. Okay. So we're going to use, it's the same, and I'll do an example of that in a minute or two. What about this lens maker's equation? It turns out that you don't have to have a nice symmetrical lens. We tend to deal with that a lot, but you don't have to have one. You could have a curvy side and a flatter side. In fact, you could have a curvy side and a flatter side. You could have a curvy side and a flat side. You could have a thing that looks like that. You could have a thing that looks like that. You could have a thing that looks like that. You could have a thing that looks like that. You can play with all these things over and over. Sorry?
What about a crescent-shaped lens?
I didn't hear the second word, sorry.
A crescent-shaped lens, like a lens that...
Oh, yes, I'm sorry, well done. You can have that. You can have that. And you can have that. That. And I can even have that. And they've got names. Plano concave, plano convex, concave convex, convex concave, and all that kind of stuff, etc.
For a crescent lens, how would you do the R1 and R2?
So I'm going to tell you that now. Okay. So if you're working from left to right, then the first surface you come to is designated as R1. Now, for this type of lens, R1 is then behind. But for this type of lens, R1 is in front. We have to distinguish those. So we say, well, R1 and R2 are positive if the center of curvature is at the back of the lens. So this would be positive, and this would be negative. Yep. And R2 is the back surface, and R2, then that would be a positive R2. That would be a negative R2. Just depends on, so you learn your nomenclature. And then you have this 1 over F, N minus 1, 1 over R1 minus 1 over R2. N, what do you think N is? Think about optics. What do we use N for? We gave it a special name, didn't we, earlier on? We said diamond had a particularly big N. Last chapter? Index of?
Refraction.
Yeah. So that's what N is. So if I make it a diamond, then my N will be 2.4. If I make it out of water, then my index will be 1.33. Okay? In truth, for that bit, you don't have to learn that equation, but I might give you it and say, hey, figure this out.
So what are like glasses? What's the N for glasses?
Depends. If you can buy certain polymers and they'll have a specific N. they've got proprietary materials. PPMA is like used for contact lenses, but that is even more complicated because they have to use the liquid of the eye. They use basically teardrops to actually form part of the lens system, which is why if you put the lens in and it's dry, you won't get good vision, and then you wet and it gets nice and So, but you're not going to make it out of something expensive or too heavy, you know.
So just you have to know.
You have to know how to use that equation. Yeah. Because I don't remember that equation. I say that. I probably, if you put me against the board, I could remember it, but it would be a struggle for me to remember it. And I just, I'd like you to know it's there. I don't mind giving you it as a question, but I will. So know what the letters stand for another sign convention. Okay. This is the science of paperweights. Those glass paperweights. That's kind of what it's probably got some very important technological aspect that I know nothing about. So I'm probably showing my ignorance, but I'm not. So I don't worry about that. Just know it's in your book. So know it's in your book. And let's stop there.